And your microphones here are push to talk. So when you need to talk, make sure those are on. There's a blue light on them that will come on.
Good morning. Can you hear me okay? Okay, I'm Charlie Price. This is Vincent Howard. And we got Jeremy Yeagle online. Okay, you gonna run that? Yeah. Okay. Okay. Vincent and I are going to be up here for 2 hours. But the good news is we guarantee you a break in between the two, the paper and the panel that we're going to have. And we'll have more help on the panel. And we'll introduce ourselves more detailed at the panel meeting. But I do want to talk about Jeremy. He worked here for the last several years as a NASA co-op. He finished his master's degree at the Indiana University of Pennsylvania this summer, and he got recruited by some company called Langley NASA Research Center. I'm kidding here, but he did go to work full time with NASA Langley. To our regret that we lost him, brilliant mathematician, and he'll be giving us some details on the mathematical foundations of vision systems later in this presentation. Okay, we're going to go, the topic here is the challenges of sharing vision systems for space missions. And our agenda is we're going to talk about a couple of advanced missions that you probably have heard about and discuss them in a little bit of detail. And then we'll get into a fairly detailed discussion of what we mean by robotics vision-driven closed-loop control. And then given that, we'll discuss the challenges associated with assuring such vision systems that we'll be talking about here. And then we'll be addressing what we've done to meet these challenges. And then we'll have wrap up and takeaway. And we welcome questions from you. If we say some sort of an acronym, please don't sit there and wonder what we're talking about. That's our fault. Feel free to interrupt us with a question about what we're talking about. But we will have a period at the end of each of these, both the paper and the panel, for a lot of Q&A. And so ask us questions then as well. Okay, the two missions we're going to talk about, you can find details at these two websites. It's all public knowledge that we'll be talking about here. But the first one is the Asteroid Redirect Mission. Now, we've heard about this for the last several years. It's an initiative from the President, and it consists of two missions, the first of which is a fully robotic mission to move an asteroid to lunar orbit. And then that is to be followed by a human mission where the astronauts will be sent to lunar orbit using the advanced launch system that is under development. And they will do detailed inspections and scientific inspections of the asteroid there in lunar orbit. This will also give them practice for deeper space missions such as human initiative to go to Mars. The next mission you may be more familiar with because it's been announced as a go. That's the Mars 2020, the next Mars Surface Rover mission. And here at IVNV, we are in the initial stages of planning the IVNV project that will address that mission. Okay, next chart. Now, here are a couple of images here. I want to talk about each of them in sequence here. There's been a considerable amount of work going into the asteroid redirect mission with teams at Crisscross NASA have been working together for the last couple of years. What you see in front here is two design options that are currently being traded off with, I believe, and a decision between them being planned for within the next 6 months. Okay, design option A would encase an asteroid and rigidize the spacecraft through this intermediate mechanism to form a structural solid combination there, so that then thrust could be applied and move the asteroid. It'd be a low thrust engine concept, and they would fly the asteroid back to lunar orbit. And what you see there is something that looks like a large coffee can approaching a rock, and behind the coffee can you can't see much of the spacecraft, but you can see one of the solar panels. And then there's a green light that looks like a laser shooting it, and frankly it looks like it's shooting right through it to me. It is not. The concept is that that would be some sort of a ranging device. Benson's immediate reaction was it's a tractor beam and it's going to pull the asteroid into the can. Maybe we are, but we'll have to wait and see if that's really true. Okay, so the coffee can is not rigid, and it will be collapsible through some sort of cables and winches so that it will completely surround the asteroid. One concept is you close the front of the coffee can and then you inflate balloons inside of it to rigidize the structure between the spacecraft and the asteroid. So those details will be forthcoming, but the point is that's one way to do it. Now the other, design option B, says let's go down to an asteroid and pluck a boulder off of its surface. Okay. Now we'll hear later in the panel about the OSIRIS-REx mission, which is kind of a precursor to this concept. Now I don't know how well you can see the spidery-looking legs over there in the lower photograph, but there's an egg-shaped looking boulder, and then there's some truss. What it looks like lightweight truss. I'm sure it's made out of titanium, so it's plenty strong. And then there's also 3 legs of the spacecraft that are touching the asteroid surface. So you have 3 landing legs, and then you have at least, it looks like, 3 grappling legs, if you will, or grappling manipulators that would pick up the boulder, and then of course the spacecraft would rise away from the surface. So those are the 2 concepts. Get a show of hands. How many people are familiar with any of this? Just give me a hand. Okay, so about half of us here for sure. Okay, now the other is much more familiar because it's very similar to Curiosity that we all know and well and love. The Mars 2020 is going to send the same class of rover to Mars, but it's going to be leaned down, so to speak, a reduction in its mass of 40%, because one of its mission objectives is to pick up samples of the surface, rocks and other size articles, and cache them for a later return to Earth by some other mission. So essentially it's a pickup truck, which we in Texas love our pickup trucks, and I noticed the guys up here in West Virginia do as well. So consider this as a pickup truck that's going to get some very valuable science information that we'll be able to bring back to Earth with a later mission. Now, from a vision system, what I read is that the The cameras will likely be similar to the Curiosity, but they have added a zoom feature on the mast such that they'll be able to look farther with their stereo vision and be able to plan pathways at a farther range. Now, let me give you a little bit of description of what Curiosity has. It has hazard cameras in the front down near the wheels and hazard cameras in the back down near the wheels. And then the mast has redundant stereo pairs for measuring distance, certainly taking images for scientific interest, but also from an engineering navigation function, you can use triangulation to get your distance that you can use for your navigation planning of where your pathways are going to go. So you can look ahead, plan your path, plan alternatives, decide on which is the optimal path, and then as you move down at your hazard cameras, you're going to make sure that you don't run into a rock that perhaps you couldn't see before you started moving towards it. Okay, and just not to go back to the previous slide, but I don't have any kind of specific information about the cameras associated with the asteroid capture. So we're just postulating that there would be cameras there to support either the encapsulation with the coffee can approach or with reaching down with the manipulator arms. Okay, now we'll talk about vision systems that close the loop for robotic control. Now, let's do a sidestep here to something that's more familiar to most people, and that's guidance, navigation, control. And that is because this is kind of a fundamental vision processing. All spacecraft are referenced to the celestial sphere for their attitude reference. And because the system will drift, periodically you have to realign the system by taking some kind of star sightings. And this is done through star trackers. And given that we know where the stars are relative to each other, and we've been studying them for thousands of years, and we've got good catalogs that represent that, then the spacecraft can be loaded with that knowledge, and then the star tracker looks for a particular star, and knowing where it is, it can refine its reference to the celestial sphere. Okay, this information is used to update the spacecraft attitude, which then ensures that when you fire your thrusters, you're pointing them in the right direction. If you didn't do this when you fired your thrusters, your orbit that you wanted to get into would not be achieved. And so it's critical, of course, to the spacecraft. So we've got a lot of people that know these systems and perform IVNV on them. Just as a historical reference, the Apollo spacecraft used optical alignment telescopes on both the command module as well as the lunar module, and they were referencing bright stars. Approximately 30 to 40 stars were in their catalog. When Shuttle came along, it used about 100 navigational stars, and the star trackers were strapped down. They didn't have any gimbaling function in them, so the astronauts would have to change the attitude of the space shuttle in order to point the star trackers at them. Of course, they had a field of view, and so they had to get the star trackers' field of view pointing at the desired star. When space station came along, the technology had changed. We'd gone to solid-state star tracker sensors, and as a result, they could see many more stars than the previous generation. And I remember that we did a reduction of a standard star catalog that had about 100,000 stars in it and cut it down to 100,000 stars for the space station to look at. Now in that case, you can have strapped down star trackers and you can just take stars of opportunity. You don't have to change the attitude of the space station. You wouldn't want to, for sure. And so that was a different generation of star tracking. Now that's been a few years ago when I was associated with that, but what I read now on Wikipedia is that currently the Russian segment on space station does track stars, where on the US segment side, we use the GPS and ring laser gyros to determine attitude. And incidentally, both those systems talk back and forth and exchange information, which I found interesting. Okay, next chart. Okay, now let's talk about vision systems. We would all agree that NASA mission systems operate in complex and dynamic environments. Okay, so in this dotted space at the top, I've got some objects over there on the left, and then I've got some actuation systems over there on the right. And so, in simple terms, NASA sends machinery into space to orbit objects of interest and also to land on them or to attach to them and manipulate them, taking samples or drilling or whatever the particular motion is that you want to do according to the mission. So these objects of interest can be simple or they can be complex. At a distance, a planet looks fairly simple. When you get close, it gets much more complex, obviously. The objects can be natural or they can be fabricated. We may want to visit something that we've put up there before, or we want to visit a new area that's all natural objects. They can be singular or they can be layered, where maybe you can't quite tell what the object is because there's another object on top of it. Or they may be cluttered. There may be a lot of objects there that you're maybe only interested in one of them, but you have to look at a lot of them in order to find that one. And the way you see those objects is through the optical spectrum. And so you're dependent on light being on those objects such that you can look at them and understand what they are. And in space, it's dynamic, so the light's going to be changing all the time. And then as you approach those objects, the geometry is going to shift because your relative distance affects how big the objects are. And so you'll need to look at them at different distances. And then all things are in motion. It may not be that apparent, but as you approach them, you're obviously relative to them. You have a relative motion between you and the object of interest. And on the actuation side, I've schematically represented at the bottom a spacecraft, in the middle a wheeled rover, and at the top a manipulator. So we've now progressed to where we can have manipulators on rovers and move towards the objects. We can have manipulators on spacecraft and move towards objects. And so the question is, what is a space vision system for? And on the next page, we assert that the vision system provides reference geometry for action. Okay, you've got to know where you are, what you're doing, what you're going to do in order to do it. Okay, and so around that, we've got a series of boxes here that describe the functionality of the vision system. So on the left, you start out with a camera and a frame grabber. Now this may all be in one box. But the two functions are separate and we've represented them that way. Okay, so the camera looks into the space and it takes an image of whatever it sees of those objects. The frame grabber, if it's a video, or if it's a still camera, you come out with an image and then you put that image into a series of vision system boxes here that we describe as vision system algorithms. Okay, so the first thing you do is you do some kind of a filtering. Typically, you throw away all the color, so you start dealing with black and white only. And then the next step is to extract features from the scene such that you can begin to, in the computer, do what we do with our eyes all the time. We want to separate the things that we're not interested in to the objects that we are interested in. And we identify those objects by identifying features associated with those objects. So if you have enough features, you can do an object identification, which is the next box. Now, it's prudent to have a reference of what you're going to look at. If you're looking for a golf ball, and you find a basketball, if you have a reference geometry in your mind of the difference between a golf ball and a basketball, then that'll be a discriminator. And so that kind of information is packed into the vision system in order that you might be able to recognize the object more easily. And then the other two things you want to do is you want to know where the object is relative to you, and then you want to know the pose of the object. Any object that you look at is going to have some sort of a principal axis. And so you want to know where that principal axis is pointing relative to you in your coordinate system. Now, in order to find the location, you may also have a world map of where the object is. For example, the rovers that land on Mars have access to all the a priori information about the Mars surface. And so it's, that information is used in order to determine where the location is. Now, all of this is fed into the path planning, and then that goes into the command generation, and you have other sensors such as the IMU or Laser Ranger that's not on this chart, but it would fold into the command generation, and then you send the execution, and off you go. Okay, a lot of words there, but that's what we're talking about here. Go to the next chart. Now, here's an example that we did in the lab that we've set up, where on the left, Vincent is holding up an input image. Now, we started out with geometric things, simple shapes, because we wanted to understand with regard to what the accuracy of this was, as opposed to starting out looking at rocks and that sort of thing. And so the filtering box, as you see beneath it, the filtering took out all the color, and you've got, and this is a threshold filter, and so you have that resulting image there. Now that image is then put into the feature extraction, and you see that the feature extraction, we had a ellipse detecting algorithm, and it picked out these ellipses that we knew were there, but the computer didn't know it before it did this. Other kinds of algorithms are edge detectors, corner detectors, cross correlation between two images, a whole litany of different mathematical algorithms in this domain of vision systems, which incidentally has been under development for 30 years or more. Now, the last image there kind of lumps in the object identification, the location, and the pose estimation. And you see each of the ellipses are numbered because we know that that is a unique ellipse that we're looking for. So that, in a nutshell, is what the vision system does. All right, well, the purpose, well, let's go on to the next chart. Okay, so why are vision systems significant to NASA? They enable capabilities. They enable autonomous control of mechanisms in complex environments. They provide a faster response time than teleoperation or telerobotics. Now, what I mean by that is that if I have a robot that's remote from me and I have a control station here, I can either push a button or move a hand controller, and it will move because I've got an electrical wire that's running at a high rate of speed, and I can see it move. Now, if I remove that robot millions of miles away and send a command over a radio frequency, obviously we're going to have delay the farther away it gets. And when you're talking about a Mars distance, you're talking about a round trip time delay of at least 6 minutes, and that's when Mars is at its closest. When it gets at its farthest distance, it's over 40 minutes round trip. When Mars goes behind the sun in conjunction with the Earth, you lose all contact with it for 2 to 3 weeks. Okay, so if ground controllers are here trying to command the rover on Mars, they can do it and they can wait. But if you think of it as from an efficiency of time point of view, then anything that you can do autonomously on Mars based on what you know there, the more efficient your yield of science is for the time that the rover is operational. Now, Mars is the same size as the Earth, but it has a 25-hour day. And so since the rover sleeps at night, you've got half a day to do your work. So if you think about it, the efficiency in yielding the science out there is heavily dependent on how well you can automate that process. And so the vision systems are required in order to do that. And so that's where their real value comes to the NASA missions. And that's what I say in the next point. The capabilities assure that the NASA missions with long communication time delays have more efficient use of resources such as Martian daylight or downwind bandwidth and ground control staffing. I'm sure we would all like to be on the ground commanding the robot, but that is an expense that's built into the mission. The other point that I missed at the top is that if you've got a vision system remote and it's with these new multi-megapixel cameras that we have taking a lot of information, you can beam that all back down to Earth. But in order to use the bandwidth efficiently, if you can have some local discrimination among those images by a vision system, you can perhaps get more efficient with sending the information that's relevant to what you want to do in a smaller form. Okay, and then finally, when things go bad, having a vision-enabled capability to avoid collisions and other problems like that is certainly a capability that's important to us. Okay, next chart. Okay, now here's the challenges that we see for IVNV for assuring vision systems. And we've kind of wrapped these up in a few here, but there's a lot of subtleties beyond this. But to me, the key point is framing the problem space. Okay, again, the human eye and the human brain can look at a very complex room with a lot of information coming at me, and I can identify objects easily because in my brain I know what a chair or a table is or who Van is. You have to build all that knowledge into the computers in order for the vision system to work. And so how you program your machine to recognize what is relevant to your mission compared to what that camera is going to ingest, I believe is one of the main challenges. So you have to determine what is it that you want to see on this mission, what key features of the things that you want to see are there for the system to identify. And the other we've already talked about, robustness during lighting variability to prevent the functionality not being able to do. If you have a shadow, a bright, high contrast shadow occluding the object of interest or the feature that you're trying to identify, then it's going to make the identification much harder to do. And you'll miss the features, which means you'll identify the object, or you might get an incorrect estimate of what the pose or the position is of the object. And again, I believe I mentioned this, as you approach, your range is going to decrease and the relative geometry that you're going to be bringing in through the camera is going to look different because your geometry morphs the closer you get to the object. And in some cases, the light intensity will grow because you're getting closer to a shiny object. And then you'll all of a sudden see a lot of details in the image that weren't there before, and you've got to resolve how you deal with them. And then finally, the fidelity of the field testing is hard to do because it's hard to represent exactly the environment that you're going to be operating in. Okay, well, we've got some ideas. We've answered some of these questions to a certain degree, and I'm going to turn it over to Vincent for him to talk about a couple of the things that we've developed here. Okay.
So Jeremy and I are going to address the challenges for doing IVNV on vision systems. We did this at IVNV. You know, obviously our answers aren't complete, but where we created a technical reference and a hardware vision testbed system. The vision system technical reference is a domain knowledge IVNV for the IVNV analyst to use to establish the context which upon to judge the developer's vision systems artifacts. So what we have done in this technical reference is to address multiple areas. So we have addressed risks to characterize the associated risks with the vision systems and associated mitigations. I'll speak to it a little bit later about a few of them. And Charlie's mentioned lighting conditions, and that's a large one. Vision also, excuse me, vision system requirements define the critical tasks that the vision system shall carry out and the relevant information that IVNV analysts should request from the developers. We also define design analysis to characterize the operational envelope of the vision system. The operating envelope is where the where the vision system has the greatest probability of success in the mission. The it is consisted of multiple constraints where the vision system's performance is acceptable. This includes lighting conditions, types of such as spotlights, shadows, the type of lighting it will encounter, type of object that the vision system will encounter. Is it a rock? Is it a defined? What features are most prominent in the object that it will most likely encounter. The number of objects in the frame, the background, noise rejection includes camera noise, also background noise. Also, when you move an object, we automatically compensate for its different projection. But how much compensation does the vision system provide? Can account for? What's the distance that you can detect the image? Also, is it dependent on an image library that needs to be created before? So do you need to, for example, for the asteroid, do you need to take high resolution images and map the asteroid before going out and doing pose estimations? And also, a deal with spacecraft is the limited CPU resources do you have. So this must all be constrained by the CPU. This all must be done with the onboard processing power because it's no longer necessary if the control is done remotely. The number of cameras that this vision system needs. Is it a monocular system, or is it like our system? Is it binocular to take depth reading, or does it have multiple cameras? Also, the background makes a difference. So if you're looking for an asteroid in a black background with some stars, is easier to take out than if you're on the planet Mars and you're looking on the surface and you're looking for a particular rock of interest. So here's an outline of the sitemap on Confluence. This is available to the NASA IVNV community. If you want to get more details, you can come to see us to see how to access it. But there are major points that I like to address in on this slide. So we have broken it down to multiple pages. First one is risks, and we 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 identify risks that missions, different segments of missions may. So a ground-based mission, such as a rover, or a space-based mission, such as a asteroid capture, may encounter. So one example is noise, and noise can be broken up into many segments. One noise is camera noise. So if you take a picture at night, I don't know, you might get a grainy picture. So that's a Gaussian noise that's just from the photodetectors. So there are certain risks that this is a lower risk risk. So there are certain risks that this could lead to. So you could get false detection. So some of the noise could be by your vision system detected as a feature, and as Charlie pointed out, if you misdetect a feature, you may not be able to correctly identify where the object is or its orientation. There are ways to mitigate this, which is such as a canny filter is an edge detector. So if you look for the edges, you can eliminate most camera noise. You can do some smoothing. You can blur to make the noise less apparent in the image. So this one you can easily reduce its risk. Another type of noise is background noise. Background noise is not anything to do with the vision system, but it's more in the environment. So you may be looking, for example, on Mars, if you're doing route planning and there's a rock boulder of interest, but there are other boulders that are not of interest, or some boulders are hazards or clouds. So this presents a different type of risk that's mostly due to environment. So the risk associated with this is, again, false features. You can also be hiding the vision system may not be able to pick out the feature of interest or the object of interest. So image segmentation you can also use other sensors to point out. The vision system can have an estimate of where the object is in the frame, so it will only search in the area of interest. You can do that from previous information, and also you can do that from other sensors. So moving on to requirements, we define critical tasks that the system should do. One task that the system for asteroid capture is determining the pose and the location of the asteroid. Another task on Mars 2020 is route planning. So you have to the robot has to develop maps for guidance and control. We also have put a segment of information request. This is highly critical for IVNV because we need to know how the system operates and how it works in order to better understand how it functions. So we've put together a detailed list of the information, such as how does feature detection work, to what objects are we is the is the system looking for? Is it how is the filtering done? What is the constituent filters? So with, as Charlie's pointed out, that these vision algorithms are comprised of multiple filters to accomplish certain tasks. So this is important for IVNV to perform tests and make assurance statements. Design analysis covers the system architecture and how we would expect a system to perform, and also how we expect the layers of the algorithms to be ordered. Because in the example that Charlie showed, if you do the canny, the threshold detection the last, then the ellipse detector will find lots of noises. So it would be completely useless, the information from that. So the order does matter. And then we also have a section for lighting and shadows, uneven lighting. So shadows present an issue because it may hide key features you're looking for to identify, and the vision system may think of that as a feature, which is not. So pose, noise, these are a battery of tests that needs to be performed, with ground simulation, computer simulations, and also physical hardware simulations. Can the system, not other test is, can the system reinitialize? Real tracking and initialization is a different, tracking is significantly less computationally intensive, but initialization to identify what point is which point does take significantly more computational power and can actually take, significant times on the scale of seconds to minutes. So this is critical. So we've also generated, Jeremy has also generated vision system algorithm and training documents, so we can go into the details of how the mathematical theory of these algorithms, and we have a library of algorithms that the IVNV analyst can look at. So I'll let Jeremy speak for a few minutes.
Okay, can we switch over to Jeremy?
All right, can you guys hear me out there? Good morning, can you hear me okay? Am I coming through okay out there? Okay, good deal. Just needed some confirmation on that. Thanks. Good morning from Langley. Very happy to be back working with IVNV, even if it's just virtually this morning. But as Charlie and Vincent have talked about through the presentation, certainly image processing has a really significant mathematical basis. I may be a little biased on that as a mathematician, but I think that's certainly the case when you begin to analyze some of these systems. So within the technical reference, what we wanted to do was to provide a reference for analysts that really covers some of the mathematical foundations of image processing. And we wanted to organize that as a high-level overview of image processing and computer vision algorithms. As Vincent discussed, each of these algorithms, when they're actually implemented on a mission, are a multi-step process. They could become very complex. However, they're always going to be composed of basic components. And so what we sought to do was to provide a reference, again, at a high level, the 60,000 foot view, to some of the basic techniques that are smoothing and sharpening, edge detection, which is largely matrix-based mathematics for the analysts to understand and become familiar with. And then also dive down a bit deeper into multi-step processes like canny edge detection, cross-correlation, or object tracking, and also provide a focus on the potential for not only spatial domain techniques, which would be the matrix-based techniques, but also frequency domain and probability-based techniques, which as you get into some of the more difficult aspects of autonomy in these missions will certainly be something that has to be utilized. So again, the goal really wanted to help analysts understand the components of these vision techniques while they perform that assurance work. Of course, questions that are going to come up, as Vincent alluded to, are what type of missions are going to use a certain type of technique. So asteroid retrieval will use different techniques than what satellite servicing would be. And really, the particular mission requirements are going to determine a lot of the choice of algorithm. So we wanted to help provide a reference that would help analysts know which path a mission may choose to take. And also inside a particular mission, at various phases, those algorithms are going to look very different. So in a satellite servicing, for instance, the algorithms and processes used in long-range operations are going to look very different than those used in close proximity operations. And is a third layer of that, what we really wanted to do, again, from the mathematical standpoint, was provide some insight into the parameters or steps in each of these algorithms that are going to be most affected in terms of their sensitivity, if those are changed depending on how requirements are designed and what the optimal operating window is for that, the operating envelope, and really what's going to generate the most efficient outcome for that. So again, all of these, it's really a sandwich sort of approach to building these algorithms, and really having a basic understanding of where are these different parameters or variables hidden that are really going to determine processor speed and optimal envelope is what we wanted to direct analysts towards. So we also incorporated a series of very high-level tutorials in a PDF format, specifically trying to keep it to a short length to provide analysts who are new to image processing some background in fundamental concepts. And so those are designed to be maybe 5 or 6 PowerPoint slide equivalent, and give them a sense of mathematical processes like convolution, which are really necessary for image processing, some background in the probability that's used, and then also within that format of PDFs, provide them some reference to other materials that are available online, or some of the resources that Vincent can discuss in the reference table to help them drill down if that's particular to the mission that they're working on. So again, wanted to get this all in the tech reference, give a solid understanding of mathematical fundamentals, since we felt that is really crucial to working on a lot of these future missions and the type of work that analysts are going to need to be able to do with that. So I'll switch it back over to you guys now.
Okay, we are running a bit short of time here. We want to talk a bit about the test bed, the vision system test bed that we've developed. Its purpose is to evaluate the operating envelope of a vision system and measure its performance against an independent truth measurement system. And so I'd like to just go ahead and jump to the next chart. This is a diagram of what it looks like. Everything in this image that's black represents structure, and we'll start with that. There's a structural frame 8 feet on a side approximately that provides us, provides a rigid reference that we can mount the truth system cameras on. But within the structure, you see a vision camera system looking at a geometric object, this specifically being a target satellite scale model that's built by one of our summer interns. And taking that information, the images from the camera are sent up to a vision processing system in the ITX laptop at the top. That goes through an inverse kinematics and then derives commands to be sent through the RoBoard the servo commands down to drive the robotic arm. So what the interns did this summer was to develop the capability to guide the arm essentially through space to touch a prescribed point on the target satellite based solely on the vision information that came from the camera. So that's essentially a working vision-driven control loop. We started out with the physical dimensions here so that we would be able to measure it against the servo optic, truth camera systems. We haven't gotten the system measured directly yet because we're still calibrating the truth camera system, but we're midway through that. Okay. So we'll wrap it up and take questions here, but fundamentally NASA continues to push the envelope in space exploration, many dimensions. We're all proud of that and glad to be part of it. Complex operations, robotic operations are planned for the asteroid redirect in Mars 2020. There'll be vision systems for sure on the Mars 2020. I expect there'll be vision systems on the asteroid redirect as well. We've identified some challenges and we've got some mediations and work that we feel like is going to prepare us for being able to perform IVNV on these systems. Appreciate your attention. We'll take questions on the missions, robots, our vision systems, and discuss those. Okay. Hey, Art.
Thank you. On the test bed, I believe you said that you had basically everything was calibrated. The distances for the camera and the arm were eventually already programmed into the system. Or, I mean, you know the distances to everything inside your system. A particular starting point for your arm and where your camera is, right?
Right. We know where the position is based on what the camera says.
Okay.
Yeah, the camera in the bottom there is the system camera. Cameras in the top are the reference cameras. Yeah. So based on the system camera.
For your system to determine distance to your target satellite or whatever, I mean, will you need a stereo pair to do that? Or is that you have one camera right now?
One.
In your vision system?
Correct me if I'm wrong. One camera, but we use different positions
Yeah,
to
so,
effectively do a triangulation.
Okay.
Yeah. Right.
so you can also tell from the size of how much, if in this case we know the size of the model. So if you know the focal length, and then if you know, we can also calibrate based on the distance. So that, yeah, you're talking about the disparity, but you can also back out if you know some information.
Well, I guess to generalize a little bit, I mean, when you reach out to something, you know how big that water bottle is, but you know you can use cues to determine how big a rock is, without knowing how big it is ahead of time. But you're saying that well, you have a known object size now, but if you substituted, say, some sort of generic rock representing a boulder or asteroid for your target satellite, then you'd use your stereo, your generated stereo pairs of imagery to determine its size.
Yeah, you
Yes.
can do that with the stereo image, and also one way with because my experience is with NOAA is that we have one camera and we send two laser beams that are parallel, so if we know the distance, that's another way to figure out the range.
No doubt that if you augment a vision system with any kind of a ranging device, it makes it more robust. No doubt. Good morning.
Morning. The previous two Mars rovers, the Mir rovers, Spirit and Opportunity, I read up on some of the published information on the DIMES system, which was a vision system used during the descent to the Mars surface.
Right.
And I don't know if IVNV was involved in assessing that, or if you've looked at it since, but I think it would be a really good example as an illustration of a lot of the points you made on, risks and requirements and design and so forth.
Right.
So I'm just wondering if you were aware of the DIME system and what was done to essentially test it.
I'm not familiar with that particular acronym, I mean, the system represented by that acronym. Actually, that IVNV was performed by people that are here. Travis Dawson, for example, was associated with that, but that was before my shift, so I'm not directly familiar with it.
Okay, well, very briefly, it was a camera that took successive photographs of the surface,
Right.
identified a feature in the first photograph, tried to find that feature in the next one, and so forth,
Okay, right,
in order to determine the horizontal velocity from wind.
right.
So it had a lot of the aspects of
Mm-hmm.
features and noise and difference of perspective and confusion and efficiency. It's a great example.
Absolutely, absolutely. And the group that did the IVNV on Curiosity, the people are here. When that was done, we were different companies, and I wasn't directly a part of that. But yes, we've got people here that know that system.
Okay,
Right.
great.
Yes,
Thank you.
thank you.
Okay, we are going to go ahead and take our break.